And of course, thank you to Richard and Pia for giving me the opportunity to talk here today. I haven't yet started to work on ME/CFS, but we do think we have actually identified the pathophysiological basis of fibromyalgia. And I'm primarily here to explore opportunities to test our work, if it also applies in ME/CFS. And the reason we think, as obviously the chair alluded to, that ME and FMS may share the pathological basis is that they share many of the symptoms. They have many symptoms in common. So ME is, of course, characterized by chronic fatigue and post-exertional malaise with sleep disturbances, pain, and cognitive dysfunction. And a very similar repertoire of symptoms are observed in fibromyalgia, but there's an emphasis on pain rather than fatigue. So you have widespread pain with hypersensitivity associated with sleep disturbances, fatigue, and emotional distress. And we also found it quite intriguing that we see a very similar female-to-male ratio among patients. So we have about 4 times as many women as men in both conditions. So fibromyalgia is perhaps considered more common. So we have about over 2% of the world's population affected by fibromyalgia. And as I mentioned, 80% of patients are women. We also see that there's a very dramatically increased prevalence among patients with other rheumatological conditions. So if you suffer from RA, lupus or Sjögren's, you are perhaps 10 to 30% of those patients also have fibromyalgia. Just like with ME, we don't know the cause, or the cause hasn't been identified in the past at least. But there seems to be a general agreement that there's an abnormal pain processing in the brain that's responsible for the generalized pain and sensitivity that patients experience. We don't have any effective therapies, and the symptoms that patients experience has to be widespread musculoskeletal pain. So that's what defines fibromyalgia. They must have pain in the lower and the upper body parts, and in the left and the right, to be considered potential fibromyalgia patients. They also have very considerably increased sensitivity to pressure. And you can examine the upper palpation. So you apply pressure with the thumb, and if it hurts in a sufficient number of places, that's a good indication that you may have fibromyalgia. And as I mentioned, patients also experience fatigue and sleep problems, and some cognitive brain fog and similar. And it was particularly the fact that, like many other rheumatological antibody-mediated conditions, fibromyalgia is predominantly affecting women, in combination with the fact that it's a very common comorbidity with rheumatological conditions. It made us want to ask the question whether autoantibodies may be responsible and both causing and maintaining fibromyalgia in patients. And to be able to examine this in a direct way experimentally, to isolate antibodies from patients, we take a serum sample and then, using a particular column, purify one type of antibody, the IgG, from patients and administer that to mice. And then we use a battery of sensory tests to observe whether or not the mice starts to display the same symptoms that the patient experienced. And one of these tests, here's a test for cold sensitivity. So by scruffing the mouse gently, we can place one of the hind paws onto a surface, in this case maintained at 10 degrees. And then we measure how long it takes for the mouse to decide that this is unpleasant, starts to hurt. In similar tests, we can also apply pressure to the paw and measure at what force the mouse decides that it starts to hurt. And the readouts are quite clear, so it's not difficult to actually determine when the mouse decides that pain is starting. And when we start these experiments, we always compare IgG purified from patients with IgG from healthy control subjects. And we administer IgG on the first 4 days of the experiments. So we can see here in groups of mice that have received IgG from healthy control subjects that the sensitivity to mechanical pressure is completely unaffected by IgG from humans or healthy subjects. And the same with cold. So IgG per se has no impact on sensory function in mice. The other point I would like to stress is that the repeated testing that we expose the mice, we test them daily for the first 5 days, doesn't have any impact on subsequent readings. So they don't learn that this will become unpleasant at some point. They don't avoid the test. And this is in very dramatic contrast to what happens when we administer IgG from patients. So for our first patient, we were very surprised to see that already 1 day after injection of IgG, we see a very significantly increased mechanical sensitivity in the mouse. So we've transferred the tenderness that the patients experience to the mouse using a specific sample isolated from the serum. And we saw a very similar pattern using the cold test. So a significantly increased cold sensitivity on day 1 after administration of the first dose. And this was one patient. We obviously wanted to test whether it applied to more than this single patient. And when we used a second healthy control subject and a second patient, we saw a very similar profile, rapid onset and quite sustained increased sensitivity to mechanical and to cold sensitivity. And after we observed it the third time, we thought that this must be a pattern that applies broadly among patients. And since then, we've increased the sample size slightly, so we've tested 8 patients and 6 control subjects, and we haven't really seen any diversity. But every patient we have tested, we've been able to successfully transfer the sensory profile to the mouse. So there's perhaps not much, there's probably limited benefits just continuing to transfer samples from patients to mice. But the first question we're faced with whenever we present these results is, do you think that you managed to sub-select a particularly autoimmune cohort of patients? We don't think that's the case, but to address that possibility, we decided to use a slightly different approach, where we use samples from a large number of patients, and instead of using the samples pure, we pull from a patient cohort before administering the IgG to patients, to mice. And here we've done this by collaborating with the Karolinska Institute in Stockholm, who provided us with IgG from 20 individual patients and 20 control subjects. This is a test, this is actually a questionnaire question. How much pain, can you rate your pain between 0 and 100, where 0 is no pain and 100 is the worst pain imaginable during last week? And you can see that all patients report at least substantial or very intense pain continuously. So this is the spontaneous baseline pain level. So they certainly have fibromyalgia. They also have mechanical sensitivity. They're also tender. So this is a test where our collaborators have compared control subjects and patients. At what force applied, I think, to the forearm, does it start to hurt? So this test was quite similar to what we do in the mice. You apply force to a body part, you record when the patient or the mouse report pain. And as you can see, patients report that about half the intensity of force is sufficient to evoke pain. And we've, in 2 experiments, used half of the patients and half of the control subjects, pooled samples, and administered them to mice. And as you can see, in both experiments, we see a dramatically increased sensitivity to mechanical pressure in the mice. So we do think that this applies to all, or at least almost all patients. We haven't encountered any examples where this isn't the case. We also followed the time course in one of these experiments. So we administered the mixed sample. And the fact that the mixed sample works obviously means that we must have similar activities in the different patients for them to be additive and actually be active in the mouse. But when we follow the time course, we can see that if we leave the mouse, the mice to recover over a few weeks, after about 3 weeks, they have recovered normal function. So it seems if you can remove the antibodies from the animal and perhaps the patient, symptoms actually disappear. Patients experience widespread pain, but almost all tests that we use in animals are focused on the hind paw. Obviously, patients don't particularly complain about pain in the hands or feet, so we wanted to devise a test that allowed us to examine pain sensitivity in muscle. And we actually used the same device that we used to assess the paw sensitivity, but instead examined the thigh muscle of mice that had been administered with control or patient IgG. And in these experiments, you can see that, can't see the laser there. You can see that patient IgG significantly increased the muscle sensitivity to mechanical pressure as well. The most common test used in animals is a type of filament that's calibrated to bend at a certain force that you can stimulate the pore surface with. They're called von Frey filaments. And to make sure that our data are interpretable and applicable to the community, to the wider research community, we've also used this test in some experiments. And as you can see, patient IgG dramatically increases the sensitivity to von Frey stimulation as well. At this stage, I obviously was very curious to find out how antibodies may cause increased pain sensitivity in patients and mice. We turned to a preparation that allows us to study the activity of individual nerve fibers, sensory nerve fibers that either sense innocuous normal touch or pain. And in this preparation, we dissect the hind paw skin with the sensory saphenous nerve attached. We can then, in vitro, in the absence of the spinal cord in the brain, actually study the individual fibers that the body uses. We can stimulate the fibers by physiologically relevant stimuli, so we can use a computer-controlled device to probe mechanically or apply temperature or stimulate electrically nerve fibers. And if we sub-dissect the nerve into finer and finer filament, we're actually able to record the activity in single nerve fibers. And depending on their properties, we can classify them as either not likely to be involved in pain sensing, but sensing movement, normal touch, etc., A beta fibers, or into pain sensing A delta or C fibers. And when we performed these experiments, we obviously primarily focused on pain sensing fibers. So A delta, nociceptive pain sensing mechanosensitive fibers were the ones we started with. When we apply mechanical force to these fibers, you can see that we see a roughly doubling of the number of action potentials evoked in preparations from mice that were given patient IgG compared to those mice that were given healthy control IgG. So they respond with a larger number of action potentials and a higher action potential impulse frequency. And we saw a very similar pattern in pain sensing C fibers. So about a doubling of the number of action potentials evoked by mechanical stimuli to the receptive field of pain sensing nerves. And since we've studied cold sensitivity, which is a common feature in fibromyalgia patients, in vivo, we also decided to record the activity of cold sensitive A fibers in vitro. So here we stimulate the receptive field of the nerve, but not the nerve itself, with a cold ramp, and then we record the action potential activity evoked by the temperature. And in these experiments, we first of all noticed that the nerve fibers don't seem to respond to at a different response threshold. They respond to the same temperature change as in preparations from healthy control subjects, treated mice. But we do see a dramatically increased number of action potentials. And if we look at the number of action potentials fired during the application of a cooling ramp, we see that this is the case on average throughout the period. So it seems that the nerve fibers actually respond to stimulation at an increased action potential frequency throughout stimulation. And perhaps this can inform us a little bit about what type of processes may be responsible for the increased pain sensitivity produced by IgG. But from these experiments, we conclude that autoantibodies cause pain in fibromyalgia by sensitizing peripheral pain-sensing nerves. I also think it's a good opportunity to compare the profile of patients with mice, because we think we've been able to successfully transfer the syndrome of fibromyalgia from a patient to mice. And patients obviously have spontaneous ongoing pain, and we can't easily ask the mouse how much did it hurt last week. But we can examine whether they have pressure pain. So patients are hypersensitive to pressure, and we see hypersensitivity to pressure in the mice. Patients also report a reduced pain threshold to mechanical stimulation, which is subtly different. And we see an increased responsiveness to stimulation with von Frey filaments. And both patients and mice treated with IgG display an increased sensitivity to cold. And if we try to interpret our results in context or with the current paradigms in mind, we see that at the moment most investigators consider the generalized pain a consequence of altered pain processing in the brain. And the treatments that are available as first-line therapies for patients are primarily gentle exercise and strategies that make the patients more able to live with chronic pain. As we think that we show that fibromyalgia is caused by autoantibodies, which act by sensitizing pain-sensing nerves. And we also think that the approach we've used will allow us to actually study the mechanisms responsible for fibromyalgia in more detail, using the human pathogen, but in an experimental system. And it should, of course, facilitate development of mechanism-based therapies. Now, we haven't yet had the opportunity to test whether the same principles apply in ME, but I do think if we can do so, and in the event that the experiments are positive, I think we will provide EM, for example, with a good argument for when he's discussing with politicians that ME is, in fact, a biological disease that has a clear physiological basis. It's not a psychological condition. And I would, of course, like to thank my colleagues, Stuart Bevan, who will speak later, long-standing close colleague and collaborator, Ulke Kurda, who performed all the skin nerve recordings, Clive, who handled all our mice, and my collaborators in Liverpool, who provide most of the patient material that we worked on. Thank you very much.
Thank you very much, David, and time for questions.
Thank you for a very beautiful talk and for very nice experiments. I was just wondering, is it possible to use, if you have done the experiments on mice and if you do tissue examination of the after the experiments, is it possible to use a secondary antibody that's directed against human IgG to locate the process? In case in your example, you have good ideas that it should be the peripheral nerves and nociceptors, but yeah. Have you tried to do that?
We've tried, and we've examined different time points, and we've done some of this work in collaboration with the Karolinska Institute. And the clearest conclusion we have is that we don't detect any IgG in the CNS. So we don't see any antibodies in the spinal cord of the brain, but we do see it binding to some cellular structures inside and outside neural tissues in the periphery.
I could ask that if you think about this, so could there be some possibilities of using some of these in diagnostics, perhaps, or in the future, and how?
Of course, yes. That would be, if we were to devise a test based on these findings, that would be readily applicable and easy to use and at very manageable cost. Far simpler analysis than alternative methods.
Thank you very much, David.
Thank you.